so this is our final act of equilibrium. So this is our AP Chemistry lesson video for Chapter 17. It is a very, very, very long part 1. And in this video, I'm going to cover section 17.1 and 17.2. So if you notice, we're still focusing on equilibrium. Okay, so I'm not going to lie. This video, I don't know, I just hope it's under an hour. So I'm going to try to go quickly. There's a lot of math. So I'm going to try to breeze through that quickly. So if you're struggling with the math in this video, it really just means you're not good at math from previous equilibrium videos. So maybe go back and watch those first. But either way, if you don't know, this is our last day of school. All the students are gone, and I just really want to leave also, but I'm here making lesson videos. So enjoy. Equilibrium, part 3. All right, so first we're going to talk about the common ion effect. So the common ion effect states that whenever a weak electrolyte and a strong electrolyte are in solution, the weak electrolyte ionizes less than it would if it were alone in solution. So in other words, if I already have some chlorine in a solution and I try to add something else to dissolve it that has chlorine in it, less of that's going to want to dissolve because then we're going to saturate the solution with chlorine. All right, so obviously, let's just jump on into this math. So it says, what is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution? The Ka is 1.8 times 10 to the negative 5. All right, so we have acetic acid. So I know that I'm dealing with my HA yields H plus and A minus. I'm going to set up my ice chart. All right, so y'all, they told me I have acetic acid. This is my HA. They have also told me I have sodium acetate. Acetate is the A minus. Okay, so here, for this one only, I'm going to write the actual reaction right above it. So like acetic acid looks like this. And so it's going to lose this H plus, and what's going to be left over is our acetate. Okay, so that's how I can tell that these are related. It's a weak acid and its conjugate base. Now the thing is though, it gave me moles and not molarity. But it told me I have 1 liter solution. So if I divide both of those by 1, I get molarity. So in this case, I'm starting with acetic acid, 0.3 molar to be exact. Now it didn't say anything about starting with H plus. But see, here's a new thing. I'm starting with some acetate. Okay, the acetate will already be in the solution because of the sodium acetate. It is also 0.3 molar. So see, this is the first, well, it's not the first time. I think we did one other one in chapter 16 where we actually started with something on the product side. All right, the rest of it works exactly the way it did before. I subtract X from this side, so I get 0.3 minus X. I add X to both of these, and y'all, just because we've been dealing with acids and bases so long, we haven't seen any coefficients. But remember, like if this had been a 2, I would have done plus 2x. So just don't forget about that kind of stuff. Because we've been working with acids and bases for so long and everything's just 1 to 1. Alright, so this ends up being x and this ends up being 0.3 plus x. So I set up my K expression. So Ka is 1.8 times 10 to the negative 5, and that equals my H plus, which is x, times my A minus, which is 0.3 plus x. Oh, whoops. Sorry, let's talk about our exception real quick. My gosh, we don't want to do quadratic equation. Okay, my K value is very small, so I can do my assumption. So I can get rid of the minus x and the plus x, because what we're saying is x is so small that these are both practically still going to be 0.3. Okay, so I have x times my 0.3 over my 0.3. So obviously the 0.3's cancel out. And x just ends up equaling 1.8 times 10 to the negative 5 molar. And that, of course, is my H plus concentration. However, remember, y'all, you've got to read the question. If this was the AP exam, you wouldn't get full credit. Okay, if it was a 1-point question, you wouldn't get any credit because it didn't ask me for H plus concentration. It says, what's the pH? So then I say, okay, well, pH is negative log of 1.8 times 10 to the negative 5. And so for that, I got 4.74. And then just remember, pH has no units, just like K values. All right, so hopefully that wasn't too bad. It was just a totally normal ice chart. The only thing is we just started with some product also. The other thing to keep in mind is when we get to do that assumption, we can do it to both of them. Okay, that's another thing to keep in mind. We haven't gotten to see that yet. All right, so let's keep on going. And then I'll show you an easier way to do these. Let's get to that easier way. All right, so it says calculate the pH of, I'll assume you've already paused it and tried it. And so it says calculate the pH of a solution containing 0.085 moles of nitrous acid. So see, there's my HA. It tells me Ka, and 0.1 molar potassium nitrite. So there is my A minus, because of course if you take away an H from nitrous acid, you get nitrite, NO2. But remember, we're not going to use any of that stuff. We're just going to use our generic. Alright, so it tells me I'm starting with 0.085 molar HA. It doesn't tell me I'm starting with any H+, and it tells me I'm starting with 0.1 molar of my nitrite. I'm going to subtract X from here, add X, so I get 0.085 minus X, X, and 0.1 plus X. Alright, so if I look at my K value is small enough in this case to do my assumption. So I can assume, so I can say, okay, well, those X's aren't going to make that much difference. Alright, so then I set up my K expression. So Ka is 4.5 times 10 to the negative 4, and that equals my H plus, which is X, times my A minus, which is 0.1, over my HA, which is 0.085. So once I solved for X, I ended up getting 3.82, or 3.83 if I rounded, times 10 to the negative 4 molar, and that is my H plus concentration. But again, it didn't ask me for H plus concentration, it asked me for pH. So then I say, okay, well pH is negative log of H plus, which is 3.83 times 10 to the negative 4. And so once I solve, I got 3.42, just like that. All right, so this is what it looks like if you start with some reactants and some products. All right, remember your assumption works for both sides as long as your K value is small enough, which like I said, is normally to the negative 5, but on the AP exam I see lots of negative 4s, but they give you a large enough starting concentration where it still works. Remember, the assumption only works if X ends up being less than 5% of that initial concentration. All right, so let's look at this next one. So now it says calculate the fluoride ion concentration and the pH of a solution that's 0.2 molar HF, so there's my HA, and 0.1 molar in HCl. So in this case, I also have some H+, okay, because CHF and Cl are not conjugates. Okay, so in this case, I have some H+ already, and then it tells me my Ka. All right, so I have my HA yields my H+ and my A minus. Set up my ice chart. So my HA is 0.2 molar. This time my H+ is 0.1 molar, and my A minus is none. So see, it didn't tell me I have any fluoride floating around here. Okay, I got some H+ from the HCl, but I don't have any fluoride floating around. And remember, plus, we're trying to figure out the fluoride ion concentration anyway, so let me just give you a little reminder. A minus is the fluoride ion, because we want that concentration. All right, so I'll subtract X plus X plus X. It becomes 0.2 minus X, 0.1 plus X, and X. I checked, and remember, my assumption, it works for this. All right, so then I set up my K expression. All right, so Ka is 6.8 times 10 to the negative 4. I can do my assumptions. I can get rid of this and this. So H plus is 0.1 times my X over my 0.2. All right, so I solve for X. and that'll give me my fluoride ion concentration, which in this case is 1.36 times 10 to the negative 3 molar. Okay, and that's of my F minus, because X is this. But notice it doesn't just say calculate fluoride ion concentration, it also says calculate pH. Well, pH does not come from F minus. pH comes from H plus. Well, we already decided H plus is practically 0.1. So I say, okay, well, pH is negative log of 0.1. And so once I do that, I get a pH of 1. Just like that. Okay? So, let's have you try one that's similar. The next one will be similar. And then we'll learn, like I said, one of my favorite gateways. It's called Henderson-Hasselbalch. We'll get there. Alright, so I'll assume you paused it, tried it. Let's look at it together. It says calculate the formate ion concentration. Okay, so remember that's going to be my A minus. And pH of a solution that is 0.05 molar formic acid, so there's my HA. And then it tells me what the Ka is, and 0.1 molar HNO3. Well, formic acid doesn't have anything to do with nitrate, so this is also going to produce H+. Okay, so I set up my generic formula. So it tells me my HA that I'm starting with is 0.05. My H plus is 0.1. My A minus, it doesn't say we start with any formate. Okay, so we just put 0. Alright, I subtract X plus X plus X. So I get 0.05 minus X, 0.1 plus X, and X. I check my K value. I am good for an assumption. Alright, good for an assumption there. So that means I can get rid of this and this. So I set up my K expression. So Ka, which is 1.8 times 10 to the negative 4, equals my H plus, which is 0.1, times my A minus, which is X, over my HA, which is 0.05. And I solve for X. See, this is what I'm talking about. Like this part right here, I'm going to go super quickly through, okay? Because this isn't anything new. We've done ice charts now what seems like 5 million times. Alright, so I solved for X, and I got that X is 9 times 10 to the negative 5 molar, and that, of course, equals my formate ion. Alright, so that is, I don't even know why I wrote it like that. It's, oops, sorry. It's this right here. It's HCOO negative. I don't know why I wrote out formate ion, but anyway, I did. But either way, that's your A minus. But it also asked me for pH. Well, remember, pH comes from H plus, which we already decided is practically 0.1. So again, I do the same thing. pH equals negative log of 0.1. Well, that's the same as it was for the last question. So it still gives me a pH of 1. Okay? So what that's showing is when you have a weak acid and a strong acid, the pH is really just based on the strong acid. The weak isn't really going to make any difference in it. Alright, so hopefully you got that one right. Alright, so let's keep on going. So, section 2, we're going to focus on buffers. So a buffered solution, or a buffer, contains a weak conjugate acid-base pair. So you could have a weak acid and its conjugate base, or a weak base and its conjugate acid. Since the buffer contains both an acidic and a basic portion, it will resist a change in pH if you add an acid or a base. So if you add an acid, the base will neutralize it. If you add a base, the acid will neutralize it. So it can neutralize either part that's added. So like for example, a buffer might contain HF, which is a weak acid, and F minus. And the way we add F minus is you can just add it as a salt. So like NaF will split up into Na plus and F minus. So if I mix hydrofluoric acid and sodium fluoride, I'll get a buffer. So if we add acid to a buffer made of acetic acid and sodium acetate, the following reaction would occur. So if I add acid to acetic acid and sodium acetate, the acid is not going to want to react with the acid. It's going to want to react with the acetate because remember that's the conjugate base. Okay, so the acid will react with the conjugate base. So Acid is just going to be represented as H plus because that's the important part. Acetate is C2H3O2 minus, and that's going to form acetic acid. So it will neutralize that H plus that's added, because see, now the H plus is no longer floating around to decrease pH. It's now bonded to something. Alright, the added acid, H plus, reacts with the conjugate base, which is the acetate ion, to neutralize the acid. On the other hand, if I added a base, that would react with the acetic acid. Okay? So if we add a base to a buffer made of acetic acid and sodium acetate, the base will want to react with the acid. Alright, and so this would occur. So here's my acetic acid base, we're just representing as OH minus, and so the H and OH will make water, and then we'll be left over with that acetate conjugate base. So the added base, the OH minus, reacts with the weak acid, acetic acid, to neutralize the base. Okay, so if you add an acid, it'll react with the conjugate base. If you add a base, it will react with the weak acid. So let's talk about some calculations. So this is where our favorite person in the world is about to save us from some ice charts. So when calculating the pH of a buffer solution, we can go through the long ice chart method, or we can use the Henderson-Hasselbalch equation, which, by the way, is on your formula sheet. So it says that pH equals pKa plus log of the concentration of base over acid. Now, of course, these have to be conjugates. Okay, so a lot of times you'll see it written like this, A minus over HA, like that, because that's showing that it's a conjugate set. All right, so it has to be conjugates. And so instead of doing the ice chart, we can just do this. So an ideal buffer contains equal concentrations of the weak acid and the conjugate base. And it doesn't have to, but that's just the ideal buffer. When the concentrations are equal, the Henderson-Hasselbalch equation shows that pH is pKa. So if we go back here, if these are equal, let's say it's 1 and 1, or 2 and 2, or 0.5 and 0.5, log of 1 is just 0. So if this whole thing is 0, you can see pH equals pKa. So let's look at one together. So instead of doing a super long ice chart, we can just use Henderson-Hasselbalch. So it says, what's the pH of a buffer that is 0.12 molar acetic acid, so here's my HA, and 0.1 molar sodium, I just said acetic acid, it's lactic acid, and 0.1 molar sodium lactate. So here's my A minus. So see, you'll see that the words look similar. Okay, so here's my acid, clearly because it says acid. Here's my conjugate base, and then it tells me what the Ka is. Alright, so I know that pH equals pKa plus log of my A minus over my HA. So I just plug in. So pH equals pKa. Remember, P always means negative log. Alright, so negative log of Ka, which is 1.4 times 10 to the negative 4, plus log of my A minus, which is 0.1, over my HA, which is 0.12. And since pH has no units, you'll notice I just dropped my units. So once I do that, instead of doing a super long ice chart, I just plug some stuff in a calculator and get 3.77. This is why we love Henderson-Hasselbalch. Like, if you realize it's a buffer, just count your many blessings, because it saves us from doing a whole ice chart. Okay, so let's see if you can plug into Henderson-Hasselbalch, which hopefully you can. It is literally basic math. Alright, so I'll assume you pause this one, tried it, and we'll look at it together. So it says calculate the pH of a buffer. Now, on the AP exam, y'all, they're not necessarily going to tell you it's a buffer. You would need to know that, because I would see benzoic acid and sodium benzoate, and I'd be like, wait a minute, that's a weak acid and a conjugate base. Alright, so calculate the pH of a buffer composed of 0.12 molar benzoic acid, so there's my HA, and 0.2 molar sodium benzoate, so there's my A minus. And it tells me Ka is 6.3 times 10 to the negative 5. Now what if they had given us Kb instead? We can't plug that into Henderson-Hasselbalch, but we could do the Ka times Kb equals 1 times 10 to the negative 14 and solve for Ka instead. Alright, so we have pH equals pKa, which is negative log of Ka, which is 6.3 times 10 to the negative 5, plus log of my A minus, which is 0.2, over my HA, which is 0.12. And so once I solved for that one, I got 4.42. See how easy that was? Oh man, I wish I could say the rest of this video they were going to be this easy. I really do. I wish I could tell you this was the end of the video, but it's not. So let's just keep on going. All right, so next it says how many moles of NH4Cl must be added to 2 liters of 0.1 molar NH3 to form a buffer whose pH is 9. Assume the addition of the NH4Cl does not change the volume of the solution, and it gives me the Kb of 1.8 times 10 to the negative 5. All right, so let's look at this one real quick. Let me get on the right page so we're not having to waste time with me doing math here. All right, so y'all, what we have is a Kb. Okay, so remember my generic formula for Kb is base plus water gives Hb plus OH minus. All right, so on this one, like what they're telling me is that the pH is 9. Okay, so figuring out anything else besides H plus is not helpful. Like H plus is not helpful, but I can get from pH to OH minus. That would be helpful. Okay, so if my pH is 9, I said, okay, well POH is 14 minus 9, which of course is 5. And then I said OH minus is 10 to the negative 5, which is just 1 times 10 to the negative 5. All right, so that tells me what my OH minus is. So it's 1 times 10 to the negative 5. All right, so it also tells me that we have added it to 0.1 molar NH3. So I already know my NH3 is 0.1 molar. We don't care about water, all right? And so all we have left, of course, is my HB positive. But remember, these are 1 to 1, so it's just 1 times 10 to the negative 5. All right, so then I just set up my Kb formula. So we set it up, and so we don't know this. This is not my equilibrium. Sorry, this is my initial. So I just set up my Kb. So my Kb is 1.8 times 10 to the negative 5. And that, of course, equals, I don't even know what's happening at this point. I'm sorry, y'all. I'm just tired. Okay, we don't actually know this value just yet either. So anyway, let's plug in what we do know. Okay, so we don't know our HB plus yet. Okay, remember that's what we're trying to find. We're trying to figure out how much of the NH4. Okay, this right here is my HB plus. All right, so I'm going to put in an X for this. All right, my OH minus we have decided is 1 times 10 to the negative 5. And then, sorry, as I had earlier, my B is 0.1. So once I solve for X, I end up getting 0.18 molar. That is how much NH4 positive. Okay, remember you got to be careful because like if for instance this had a parentheses and a 2, it wouldn't be equal to the concentration of this. But because it is 1 to 1, that is equal to the concentration of NH4Cl. Alright, but the problem is it didn't ask me for molarity, it asked me for moles. Okay, so you always got to make sure you're getting to the answer. So moles is molarity times liters. Well, we just figured out the molarity was 0.18, and then my liters is 2. It told me 2 liters right there. And so I got that it took 0.36 moles of NH4Cl. Alright, so you'll notice on this one I didn't do like the full ice chart because I'm trying to get y'all to kind of start being able to do a little bit of that in your head. Okay, where you don't necessarily need to write it out all the way. Like on the next one I'm going to show you, I'm not even going to put the ice chart at all. I'm just going to kind of label it in the problem to see if we can get you to where you don't necessarily have to draw one every single time. Like you can draw one every single time if you need to. Obviously, remember I told you there shouldn't be that many of them, but anytime you can save time on one question, it gives you more time on another question. Just think of it that way. All right, so y'all try this one. I will assume you've paused it and tried it, and let's look at it together. So it says, calculate the concentration of sodium benzoate that must be present in a 0.2 molar solution of benzoic acid to produce a pH of 4. Ka is this. All right, so we have our HA. So our HA is right here. So this is my HA concentration. All right, sodium benzoate, that is my A minus. So in other words, I'm looking for A minus question mark. That's what I'm looking for. It tells me the pH is 4 and the Ka is 6.3 times 10 to the negative 5. So from pH, I can get to H plus. All right, so I say, okay, well, H plus is 10 to the negative 4, which is 1 times 10 to the negative 4 molar. All right, and then I just plug in. So Ka equals H plus times A minus over HA. All right, so I take my Ka and I do 6.3 times 10 to the negative 5 equals my H plus, which I decided is 1 times 10 to the negative 4, times my A minus, which I don't know, which is just X, and then over my HA, which is 0.2. So once I solve for X, I end up getting 0.126 molar. All right, and this is of my benzoate, which sodium is positive 1. So that means there is 1 benzoate. So that is the concentration of my sodium benzoate. And this time it just asked for concentration, so that's why I didn't have to go back to moles. All right. Oh my. Hopefully you got that right. Let's see how many more slides there are of this. Oh, this is my 3rd video today, so I'm not gonna lie, I'm getting tired. All right, so buffer capacity. Guess we're not done yet. So buffer capacity is the amount of acid or base that the buffer can neutralize before the pH does begin to change drastically. So like when you add acid to a buffer, the base component will neutralize it, but it can only neutralize it until the base component runs out. Okay, so in other words, the more acid and base you have, the higher the buffer capacity. So the greater the amounts of the conjugate acid-base pair, the more resistant the ratio of their concentrations and the pHs to change. So in other words, if I have a 0.1 molar and 0.1 molar, that won't neutralize as much as a 0.5 molar, 0.5 molar. Okay, so the more you have of each of them, the more acid or base it can neutralize. So the higher the buffer capacity. So the pH range of a buffer is the pH range over which the buffer acts effectively before it starts changing pH drastically. Since buffers are most effective when your acid equals your base and pH equals pKa, then we pick a weak acid with a pKa closest to the desired pH. So like if we want to make a buffer of 3 with a pH of 3, we pick a weak acid where the pKa is closest to 3. So that's how you know which acid to pick when you're trying to make a buffer of a specific pH. When a strong acid or base is added to a buffer, we assume that it is entirely consumed as long as buffer capacity is not exceeded. There are 2 steps to calculations involving the addition of a strong acid or strong base. So now what we're going to do is we're not just dealing with the buffer alone, we're going to add an acid or a base to the buffer. So the first step is stoichiometry of the neutralization, and the second step is equilibrium calculation using Henderson-Hasselbalch. So notice I didn't say using ice chart, we get to use Henderson-Hasselbalch because there's going to be some weak acid and some conjugate base left. It's just not going to be equal amounts anymore. Not that it has to be equal to begin with. Okay, so let's look at the first one together. Oh man, hopefully we're getting near the end here. So it says a buffer is made by adding 0.3 moles of CH3COOH and 0.3 moles of CH3COONA to enough water to make 1 liter of solution. The pH of the buffer is 4.74 and the Ka is 1.8 times 10 to the negative 5. Calculate the pH of this solution after 0.02 moles of sodium hydroxide is added. Okay, so y'all, what I have to do is I have to go ahead and get rid of what has reacted with the sodium hydroxide. Now what's going to react with the sodium hydroxide? The acid or the conjugate base? The acid. So in other words, this and this are going to react until it's neutralized. So we write what my students in the past have coined as the BA chart. Okay, so we have the ice chart, so now we got the BA chart, and that's when you are adding an acid or base to a buffer. Okay, so I'm actually going to write the actual reaction happening this time, because sometimes once we start combining things, you'll have a little bit of trouble with that. Okay, so we're going to take our acid, and we're going to react it with the NaOH. But remember, the Na is not the important part, so I'm just going to put OH minus. Alright, what that's going to do is that's going to neutralize. Alright, so we neutralize by the H plus and the OH minus making water. And then what we have left is this right here, our conjugate base. Alright, so we call it the BA chart because it's before the addition itself, and after the addition. Okay, so that's what my students call it, the BA chart, because it's before addition, after addition. Alright, so before the addition, I have 0.3 moles of the acid. Okay, so I'm going to put 0.3 moles right here. Before the addition, it doesn't tell me I have any OH, so I start with 0. Water, just like in the K value or the ice chart, it does not matter. And before the addition, I also have 0.3 moles of my acetate ion. Alright, so next I use my addition. So what I'm adding is the 0.02 moles of the OH minus. So this is my addition, 0.02 moles of the OH minus. So that's what was added. That is going to be consumed. So this is used up because it's going to react with this. So all 0.02 moles are going to react with 0.02 moles of this. So I subtract 0.002 moles of this, and so once I do that, I got 0.028 moles. This is all used up. See, all of it's going to react, so I end up with 0 moles. Okay, I know that part seems weird. Okay, and so then over here, for every one of these that reacts, I'm going to get one of these because it's going to take away a hydrogen from this. So over here, I actually add the amount. All right, and so that gives me 0.32 moles. All right, so let me just explain this BA chart again because it's kind of tricky because it's different from an ice chart. So once you know what your addition is, that whole addition is going to be used up. So like it's going to be used up and you're still going to end with 0 because I have enough moles of acid to neutralize that amount. Alright, so that means I subtract that amount from the acid, so that way I'm left with the 0.028. But on this side, I'm going to add that much because remember, every time these react, I'm going to make one of these. Alright, and so then this is why we can go Henderson-Hasselbalch, because what do I have left? I have some HA and I have some A minus. Whenever you see you got HA and A minus, Henderson-Hasselbalch that thing. Okay, so we got pH equals pKa, so I do negative log of my Ka, which is 1.8 times 10 to the negative 5, plus my log of my A minus, which we decided was 0.32, over my HA, which we decided was this should not be 0.028, this should just be 0.28. Ooh, oh gosh, y'all. Fix that. Obviously, I copied my answer wrong. 0.28. Alright, and so once I did all that, I ended up getting 4.80, just like that. Alright, and then real quick, y'all, just pointing this out. Notice I ended with moles here. The reason I just plugged it directly into here was it told me I had 1 liter. Okay, so those were my molarities, because if I divide each of these by 1 liter, that is molarity. If it had been 2 liters instead, I could have divided both by 2 before I plugged in. Alright, so Henderson-Hasselbalch, anytime you can. If you got a buffer, you can Henderson-Hasselbalch it. Actually, the last 2 that I showed you a minute ago, you could have Henderson-Hasselbalch those things. I just chose to do kind of an ice chart instead. Like ice charts work, but you can Henderson-Hasselbalch a lot of things. Alright, so let's look at part B together real quick. So it says, for comparison, calculate, so what we just got since we're comparing, was we just got that the final pH, once we added that base, was 4.69. What? Oh, no we didn't. We got 4.80. Alright, and that was when we added, our sodium hydroxide, so it was 4.80. So it says, for comparison, calculate the pH that would result if you just added 0.02 moles of sodium hydroxide to 1 liter of pure water. So in this case, we don't have a buffer, so let's see what would happen to our pH there. So here we have 0.02 moles. Well, we're in 1 liter, so this really is my molarity of OH, which, of NaOH, which because it's 1 to 1, equals my OH minus. Remember, you always have to be careful because if it's not 1 to 1, you might need to multiply or divide by a coefficient depending on what direction you're going. So once I know my molarity of OH, I can choose my pH squared. Okay, so what I chose to do was say, okay, well pOH is negative log of OH minus, or 0.02, and so I got 1.7, and then I said pH is just 14 minus pOH, which is 1.7, and I got 12.3. Okay, so see, there's the difference. If I added the base to the buffer, it's only 4.8. If I add the base to pure water, it's 12.3. Okay, so you can see how the buffer consumed some of that base and kept the pH from changing a lot. Alright, so now you get to try one of these long things. Okay, so y'all try this one, and then I'll assume you've done that, and let's look at it together. So it says, determine the pH of the original buffer described in sample exercise 17.5 after the addition of 0.02 moles of HCl. Okay, so real quick, let me just do 17.5. So this is where we had the 0.3 moles of the acetic acid and the 0.3 moles of the sodium acetate. But this time we're going to add 0.02 moles of hydrochloric acid to it. Okay, so because I'm adding an acid, that's going to react with the acetate, not with the acetic acid. So I take my acetate and I add, remember we're not worried about the Cl, just the H+. Alright, and what that's going to give me is HC2H3O2. It's going to give me my acetic acid. Okay, and so then I set up my bar chart. So it told me, oh gosh, since I don't have it, let me see it on my paper. It told me I started with 0.3 moles of this. It told me I didn't start with any H+, and it told me I started with 0.3 moles of this. So we are adding 0.02 moles of my H+, but see, that's going to be used up. Okay, so it's still going to end up being 0. All of that's going to be neutralized because it's going to react with that conjugate base. So then I subtract it from the conjugate base, and so that leaves me with 0.28 molar. But here I'm going to add it to my HA, my acid. So that's going to give me 0.32 moles. Alright, and so then it told me what my Ka is. So notice I have some acid and some conjugate base. Now notice y'all, this is the HA and this is the A minus. Okay, don't mix them up. Alright, so I just plug into my Henderson-Hasselbalch. So pH equals pKa, or negative log of, what was my Ka? It told you in the previous part, it was 1.8 times 10 to the negative 5, plus log of my base, which is the 0.28, over my acid, which is the 0.32. Okay, this is kind of our backwards reaction. You know how normally we write the acid as this right here? But this one is backwards. It's the conjugate base reacting with hydrogen to make the acid. Alright, so just be careful of that. And so once I solved, I got that pH is 4.69. So hopefully you got that right. Okay, then part B, it says determine the pH of the solution that will result from the addition of 0.02 moles of HCl to 1 liter of pure water. So in other words, we're in 1 liter, so this is just molarity. So we have 0.02 molarity of HCl, which is going to be 0.02 molarity of H+. Remember, we got to make sure it's 1 to 1. Once I know H plus, I can get pH. pH is negative log of H plus, or 0.02, and so that gave me 1.70. So see, in the buffer, it went to 4.69. Without the buffer, it went all the way to 1.70. Okay, so remember, the buffer is there to neutralize some added acid and base, whereas water by itself is not a buffer, so it can't really neutralize anything added, so its pH changes drastically. Oh my gosh, thank goodness, we are done. Hopefully that video was not as long as I just felt like it was. And so y'all, you just gotta keep going. Remember, if you see acid and conjugate base, try to Henderson-Hasselbalch it. It might save you an ice chart. Okay, but otherwise, we're still deep into equilibrium. And so remember, y'all, you can do this. Let's just take it one video at a time.